In this guide, why passwords can be phished and passkeys cannot, how the FIDO2 registration and authentication ceremonies work, what the authenticator assertion looks like on the wire, and why passkeys are now mandatory in NIST AAL2 guidance. Identity Expert, powering you to be an expert in identity. Today we're covering passkeys, the W3C WebAuthn standard that replaces passwords with public key cryptography. In 2026, 80% of data breaches still involve stolen or weak credentials. We have had passwords for 60 years, and they keep failing in exactly the same ways. SMS one-time passwords and authenticator apps helped, but attackers learned to relay those codes in real time. A fake login page captures your OTP the moment you type it and replays it to the real site before it expires. Passkeys do not patch over these weaknesses. They remove them entirely at the protocol level. By the end of this video, you will understand exactly why a passkey cannot be phished, what happens inside your device when you register one, and what the biggest remaining risks actually are. Before we go technical, let's make this concrete with an image. Think of a passkey as a house key that can only be copied by your biometric, your fingerprint, or your face. There is no locksmith who can duplicate it. The blank does not exist anywhere except inside a tamper-resistant chip in your device. Now imagine that each copy of that key only works in one specific house, the lock is matched to the key at the factory, and the two are registered to each other. A fake house, a phishing site that looks identical to the real one, has the wrong lock. Your key will not turn, the door stays shut. You cannot be tricked into unlocking the wrong house because the key physically cannot operate a different lock. That is not a UI warning, that is not a user choice. It is a mechanical impossibility built into the system. That is what the RPID, the relying party identifier, does in WebAuthn. The credential is bound to your exact domain. No attacker-controlled domain gets access, regardless of how convincing their fake page looks. Let's be precise about what passkeys are fixing. Passwords have three fundamental structural weaknesses. First, they are phishable. A convincing fake login page is all it takes to steal one. The user sees a familiar interface, types their password, and the attacker captures it. Multi-factor authentication with SMS or TOTP adds a second factor, but since that factor also travels through the browser, it too can be relayed in real time. An attacker sits between the user and the real site, forwarding requests and capturing both the password and the OTP before they expire. TOTP codes are valid for 30 seconds, plenty of time for an automated relay. Second, passwords are breachable. The server has to store something, a hash of your password. That hash database is a target. Breach it, run a dictionary attack, and millions of credentials are compromised. The server is holding a secret that corresponds to yours. Third, passwords are reusable. The average person has the same password across multiple sites. One breach multiplies across every site where that password was used. Passkeys address all three. There is no password to phish. The server stores only your public key, useless without the private key that never leaves your device. And each passkey is unique to each site, no reuse, no blast radius multiplication. WebAuthn defines two ceremonies, registration and authentication. Registration happens once per device per site. Your browser calls navigator credentials create, passing a challenge from the server, the site's RPID, and your user details. Your device, the authenticator, prompts for your biometric or PIN. Inside the Secure Enclave, a new asymmetric key pair is generated. The private key is sealed inside the enclave and never exported, not even the operating system can read it. The authenticator returns the public key, a credential identifier, and optionally an attestation statement proving the key was generated in genuine hardware. The server stores the public key and the credential ID. The private key is never on the wire. Authentication works in the opposite direction. The server sends a challenge, your credential ID and its RPID. The browser calls navigator credentials get. Your device prompts for biometric again. The authenticator signs the challenge with your private key, and critically it first checks that the origin of the request matches the RPID the credential was registered for. If those do not match, the authenticator refuses. The signature goes back to the server. The server verifies it against the stored public key. Access granted without a single secret crossing the network. Here is what the actual HTTP exchange looks like. Registration starts with the server issuing a public key credential creation options challenge. It includes a random base64 URL encoded challenge string, the RPID, in this case bank example com, the user object with an opaque user ID, the list of accepted public key algorithms, algorithm -7 is EAS256, algorithm -257 is RS256, and authenticator selection requiring a resident key and user verification. The client calls navigator credentials create with those options. The authenticator returns an attestation response. The most important field is client data JSON. which decodes to a JSON object containing the type WebAuthn create the original challenge value and critically, origin set to the exact origin of the page that called the API. The server decodes this and checks that the origin matches its expected RPID. If an attacker's page called the same API from evilbankexample.com, the origin in client data JSON would say evilbankexample.com and the server would reject it. Authentication follows the same pattern. The server sends a public key credential request options with a fresh challenge, the RPID, and an allow credentials list hinting which key to use. The authenticator signs the challenge and returns an assertion. The server verifies the signature using the stored public key for that credential ID. Passkeys eliminate credential phishing and server breach exposure. But the threat model has not disappeared, it has shifted. The number one risk in a Passkey deployment is account recovery. WebAuthn is phishing-resistant, but almost every site still offers a recovery flow, forgot your device, verify by email, or confirm via SMS. That recovery path is not phishing-resistant. An attacker who cannot phish your Passkey can simply trigger the recovery flow and phish that instead. Recovery must be treated as an authentication ceremony of equal assurance to the Passkey itself, not as a convenience bypass. The second risk is cloud sync account compromise. Synced Passkeys, those backed up through iCloud Keychain or Google Password Manager, move with your account. If an attacker compromises your cloud account credentials, they may be able to restore your Passkeys to a device they control. The security guarantee shifts from device-bound to account-bound. For high-assurance scenarios, device-bound Passkeys or hardware-roaming authenticators like UBI-keys should be used instead. Third, malicious authenticator attestation. A rogue or cloned authenticator could generate valid-looking key pairs. Relying parties that require high assurance should verify attestation against the FIDO metadata service to confirm the authenticator's provenance. Fourth, post-authentication session hijacking. Once WebAuthn succeeds, the application issues a session token. That token is a bearer credential. Protecting it requires the same defenses, secure cookies, short expiry DPoP binding, that apply to any token-based system. As of 2026, the Passkey ecosystem has reached a tipping point. NIST Special Publication 863-4 elevated synced Passkeys to Authenticator Assurance Level 2, the level required for most government and financial applications. This is a significant change. Previously, cloud-synced credentials could not meet AAL2. Google, Apple, Microsoft, GitHub, Amazon, and PayPal now offer Passkeys as the default registration path for new users. The FIDO Alliance Credential Exchange Protocol (CXP) defines an encrypted format for moving Passkeys between password managers. This solves the vendor lock-in problem. If you want to move from iCloud Keychain to a third-party manager, you can export your Passkeys in a standardized encrypted envelope and import them. CTAP 2.2 added the hybrid transport, a QR code and Bluetooth flow that lets your phone act as a roaming authenticator for a laptop. You scan a QR code on the laptop, confirm on your phone, and authenticate, no USB required. WebAuthn Level 3 added conditional UI, which surfaces Passkey suggestions directly in the username autofill, making the experience as frictionless as a password manager. Next on identityexpert, TOTP, time-based one-time passwords, how they work, why they are still phishable in 2026, and what that tells you about when a Passkey is non-negotiable. All primary sources cited in today's guide are listed on screen. You'll find direct links to the RFCs and specifications in the video description below. If this breakdown helped you understand the topic better, please subscribe to identityexpert. We publish a new protocol deep dive every week. Thanks for watching. If there's a specific identity standard, authentication flow, or security protocol you'd like us to cover next, drop it in the comments below. We build our content based on what the community asks for. Subscribe and hit the bell so you never miss an episode.